Alright, so let's start with our first example. Our first example is called a binomial distribution. And in order to know that a binomial distribution is an appropriate way to model this, we need to have a fixed number of trials. So think of it as n, as the number that we're going to try here. And there's two possible outcomes in each trial. We can call one of them a success and the other one a failure. And that doesn't necessarily mean that one is good and the other is bad. It's just that we're defining one as in one direction and there's only one other possibility. That's where the bi in binomial comes from. It's two options. Alright, once we have a fixed number of trials and two possible outcomes, one we call a success, the other we call a failure, we also need those trials to each be independent and repeated using identical conditions. So nothing changes from one trial to the next. Okay? If I'm looking at a situation like that, I call it a binomial distribution. So an example is flipping a coin. There are two possible outcomes of flipping a coin. So if I flip a coin, say 10 times, then that's a fixed number of trials with two outcomes. I could call heads success and tails failure, or vice versa, whichever way I prefer to look at it. And each of those coin flips has to be independent. As long as those two things are true, then I can use a binomial distribution to model that situation and to compute the probabilities. Okay? And we'll find it lines up not just with the ones we just did with two coin flips. That's not too hard to construct manually. But I can also do it with 100 coin flips, which would be a lot harder to do on paper. But if I understand the binomial distribution, it's easy to do directly because these formulas will line up and allow me to do it instantly. Another example, shooting a free throw. So inadvertently, we saw an example of that in the sample exam. We could actually represent that using a binomial distribution, and it would make our work a little easier. In fact, it would make it easier to consider higher numbers of free throws, which in fact we'll do in just a few minutes. Okay, so that's the binomial distribution. Two possible outcomes, a fixed number of trials, and each trial is independent of the others. Okay. When I have that, then I consider this a binomial experiment if I'm doing this, and the distribution that it follows is called a binomial probability distribution. And the notation I use is n for the number of trials, p for the success probability, the success rate, and q for the failure rate. Now sometimes I don't need to write this q because obviously if there's only two outcomes, p and q have to add up to 1. Right? They should cover every possibility. And so really q is the same as 1 minus p. It's its complement. Because of that, we don't necessarily need to write down q in every case, and so we'll keep at least n and p as our key parameters. One of the things you'll find as we do these distributions, you need to have a set of parameters to describe a particular instance of the distribution. So if I am flipping a fair coin 10 times, I need to know how many times I'm flipping it, and I also need to know whether it's fair or not. If I know those two things, then that will tell me what that distribution looks like. So this is how we will describe the distribution in writing. I will say that the random variable x behaves like a binomial distribution with parameters n and p. So if you ever see this notation, it means it's binomial. This is the number of trials, and this is the success rate on each trial. Okay. Again, once I have that, I can use that information to compute different probabilities, and to compute the expected value, and to compute the variance, and the standard deviation, and so on. All of those things will come straight out of knowing these two parameters. Give you a second to write this down. At any point, if you see a notation like this that you're not sure what it means, please interrupt me. I'm more than happy to explain it as often as needed. After a while, you'll just recognize it, and that makes it a lot easier once you do. Ready? Okay. So I'm going to take a slight detour. This is really just to remind you of something we saw, I guess it was a couple weeks ago at this point. A binomial coefficient. N choose R is often how we describe that. It's a way of calculating how many ways I can select a group of R objects out of a group of N to begin with. And that's where order does not matter. So you remember when we did the poker probabilities, for instance? What's the probability I select 3 jacks out of the 52 cards in the deck? It'd be 52, 3 particular jacks. It'd be 52 choose 3. Okay. And so the way it was calculated, if you'll recall, n choose r was n factorial over r factorial times n minus r factorial. So specifically, this example tells us 7 choose 2, binomial coefficient with 7 as n and 2 as r, tells us the number of ways to pick 2 items out of 7 total. So out of 7 total items, I'm picking a pair. How many distinct pairs could I choose? And it turns out there's 21 of them calculated in this way. Another thing I wanted to remind you, when you compute this is simply writing that formula down, 7 factorial over 2 factorial, 5 factorial. Remember, factorial is just multiply from that number all the way down to 1. So this is 2 times 1, and this is 5 times 4 times 3 times 2 times 1. And the same thing for 7. It goes from 7 all the way down to 1. When you write it this way, you can see some quick cancellations. So here, to calculate some of these, if n and r, or n and n minus r, are close, if they're almost the same number, then you'll get most of it to cancel. So in this case, 7 and 5 are pretty darn close. Everything from 5 on cancels instantly. I can see all of these will be canceled out. And 7 times 6 over 2 is pretty easy. That's 42 over 2. That's where the 21 comes from. Okay. All right, so that's just a single example. But the key idea is that this binomial coefficient tells me how many different ways can I choose R objects out of n possible objects. Here's why I did that. The probability distribution function that we use for binomial distributions involves the binomial coefficient. That's where the term comes from, binomial. So if my variable x is binomially distributed with n trials and p is its success rate, so the same 2 variables that we used on the previous 2 slides, then the probability of a specific value, little x, is given by this formula. N choose x times p to the x times q to the n minus x. Now before I go any further, I'm going to explain what each of those pieces is doing. I have n trials, and I'm asking what's the probability x of them are successful. Well, that means out of the n, I need to choose which of those x are successful. Maybe it's the first x of them. Maybe it's the last x of them. Maybe it's x over 2, and then a big gap, and then x over 2. There's lots of different ways I could organize the count of exactly x of those. This tells me how many ways I could pick which ones were successful and which ones were not. Once I've done that, I need exactly x of them to be successful. The probability of that is p to the x, success rate to the x. And I need exactly n minus x of them to be unsuccessful. That's q, the n minus x. If you want to use the same notation I was using on paper before, this is like drawing out n different blanks. X of them will have p as their probability, n minus x of them will have q as their probability, and there are n choose x different ways to order the p's and the q's. So that's what that's doing. It's counting all of those things together. So remember when we did the coin flip and we had 2 heads, 1 head, or 0 heads. And that 1 head case had 2 possibilities. Tails, then heads, or heads, then tails. Right? That's because out of those 2 things, I'm choosing 1 to be heads, 2 choose 1. There were 2 ways to do that. Well, what if I did 10 coin flips and I asked for the probability of 5 heads? Well, I could pick 10 choose 5 different ways for those heads to come up in the sequence. And each one of those would have 1/2 to the 5th for 5 heads, and 1/2 to the 5th for 5 tails. And that's what this probability calculation is going to do. It's going to calculate all of that together all at once. So here's an example with a non-fair situation, a non-even. P and Q are not the same. The probability that a 60% free throw shooter will hit 4 out of 5 free throws, if we assume each free throw is independent and so on. Well, what we do, we're looking at the probability that my random variable takes the value 4. It could be anything from 0 to 5. The success rate is 0.6, 60%. So I need to pick which 4 of those 5 this person hits. Maybe it's the first 4. Maybe it's the first one and then the last 3. Maybe it's the first 2 and then the last 2. Maybe it's the first 3 and the last 1, or maybe it's the first 4. Any one of those things are possible. There's 5 total possibilities, and if you compute 5 choose 4, that's exactly what that amounts to, 5 possibilities. In each of those cases, the 4 hits have a 60% chance of happening each, so that's 0.6 to the 4th, and the 1 miss has a 40% chance of happening, so that's 0.4 to the 1st. When you multiply all of that out, you get 0.2592, which means there's a little bit more than a 25% chance, almost a 26% chance, that this person will make exactly 4 of their 5 free throws. What do you think is the most likely outcome if you're a 60% free throw shooter? How many would that be out of 5 if you hit exactly 60% of them? Well, 60% is 60 out of 100, which is 6 out of 10, which reduces to 3 out of 5. So if you're a 60% free throw shooter, I would expect the most likely outcome would be that they hit 3 of their 5, because that'd be right in line with their average. And so that probably will be a probability just a little bit higher than 0.2592. I could also find the probability that they missed all 5. It would be 5 choose 0 times 0.6 to the 0 times 0.4 to the 5th. That'd be 1 times 1 times 0.4 to the 5th. What is 0.4 to the 5th? It's basically 0.1%. Okay, so that's going to be very unlikely. All right. So let's do this in 2 ways. Let's first consider what happens with a fair coin, and then let's see how that changes with a biased coin so we can see how this formula plays out. And what I'm going to do is I'm going to write down the formula in general first. So the probability that my random variable takes a certain value x is n choose x times p to the n times q to the n minus x. Wow, wish I'd given myself more space. Alright, and I'm flipping this fair coin 5 times. And I want the probability of seeing 4 heads. Alright. So let's see. If I'm flipping the coin 5 times, that means there's 5 places that those heads could occur. I want to find the probability of exactly 4 of them. So that's 5 choose 4. Notice that's the x value here. My n value here is 5. And this is a fair coin in the first case. I'll actually label this as the fair coin. And I want p to the n, q to the n minus x. So p is 1/2 for a fair coin. And I want 4 heads. Q, the probability of tails, is also 0.5. And I want 1 of those. So let's see. That's 5 times 0.5 to the 5th. I'm going to calculate that on a calculator because I've already made a mistake today. 0.15625. So if you were to toss a fair coin 5 times and record how many heads you got, and you did this maybe 1,000 different times, so 5,000 total coin tosses. If each time you tossed it 5 times, you recorded how many heads you got, the proportion of times you got 4 heads should be about 15.6%. That's exactly what this is saying. This is the long run percentage of the time that I would expect to see exactly 4 heads out of 5 coin tosses. Now that's when the coin is fair. Well, what if the coin is biased? And so here, let's say I have a coin that has a 75% chance of heads. So give H equals 0.75. And the probability of tails is 0.25. In that case, let's let Y denote its count of heads as a random variable. I'm using a different name so that it's distinguishable. It will be different. How do I find its probability of exactly 4 heads? Well, I go through the same process. Out of the 5 coin flips, I need to choose which 4 of them will turn up heads. And then I need exactly 4 heads, which have probability of 0.75 each, and exactly 1 tail, which has probability of 0.25. And so then if I multiply those things together, this is still 5 times 0.75 to the 4th times 0.25. Let's see what that comes to. 5 times 0.25 times 0.75 to the 4th power. So would you expect it to be more or less? A little bit more. Because a fair coin, I expect to have 2.5 heads on average out of the 5 coin tosses. On this one, I'd expect, well, 3/4 of 5, which is 15/4. So I'd expect 2.75. Is that right? 15/4. No, 3.75. 3.75. So this should be a little bit closer to 4. So I expect that to be higher. And sure enough, it is 0.3955. Almost a 40% chance that I'll get 4 heads. Again, it makes sense because heads are more likely with this biased coin. Alright, see how that looks here. Great. Okay, so those numbers match what I have in the slides. So the probability that a fair coin comes up with 4 heads is about 15.6%. The probability that this biased coin comes up with 4 heads is almost 40%. It's 39.5%. All right. Well, so in general, if we think about how to calculate that, if I flip a fair coin 100 times, how many heads would you expect on average?
The fair coin would be 50%, right?
Yeah. So if I flip a fair coin which has a 50% chance of heads and a 50% chance of tails 100 times, how many heads would I expect on average?
50.
Yeah, 50, right? Take that 50% of the number of tosses, and that's how many I'd expect on average to turn up heads. Well, what if I use that bias coin from a moment ago? 75% chance of heads. I flipped that 100 times. How many heads would I expect on average? 75. You just take 75% of the tosses and call those heads, and that's what happens on average. And so in general, if you use that same idea, if you have n trials, and p is the proportion of them that are successes, then the expected number of successes would be n times p. That's all there is. No listing out charts, no multiplying and then adding everything together. It's all just n times p. It turns out if you use those complicated formulas, you can show that this is true using the binomial distribution formulas and the formula for expected value. But you don't have to do that. It's been proven this will always work. If it's a binomial distribution, the expected value is n times p. Okay. Well, what about the variance? That's a little harder. I'm not going to prove this one for you. I'm just going to show it to you, but it's actually really nice. It's n times p times q. Or if you don't like to use q, since q is 1 minus p, it's n times p times 1 minus p. So as soon as I know the parameters from my binomial distribution, I instantly have the expected value and the variance. And then from that, of course, the standard deviation. If that's the square root of the variance, which is the square root of this formula. All right. So let's use these formulas for two very specific examples. I'm going to stick with my two favorites so far. Does everyone have a chance to write this down? I don't want to take it away until you have. All right. So the two specific examples that I'm going to have us do are 4 tosses of a fair coin. So a fair coin tossed 4 times. And the second is 100 free throws. Steph Curry. Now, he's a 90.8% free throw shooter for his career. I used these slides, or at least this example, last year, and I had the number 90.7, and I looked at it, and nope, it's gone up. Even in a down shooting year, he's raised his career average. What can I say? All right. Let's find the expected value and the variance in each case. So I'll call this one x and this one y, I guess. All right. So is this a binomial distribution? That's the first question. Well, I have a fixed number of trials. That's 4. There's 4 tosses. There's 2 outcomes. It could be heads or tails. Right? And I'm just counting the number of heads, so that's fine. And then is each coin toss independent and done under identical conditions? Like there's no hurricane force winds influencing my 3rd and 4th tosses. As long as that's true, then I can use the binomial distribution to define this. And it looks like that's a reasonable assumption here. So what's my n? It would be 4. And my success rate is 0.5. So not surprisingly, if I toss a fair coin 4 times, I expect on average to have 2 heads and 2 tails. I do this over and over and over again. In the long run, this would be the average outcome. All right, what's the variance? Well, that formula is n times p times q, which is 4 times the success rate, So the probability of heads times the failure rate, probability of tails. And because it's a fair coin, these two things are the same, which makes my life even easier. 4 times a half times a half is 1. Alright, so that's the expected value and variance for 4 tosses of a fair coin. What if I'm looking at Steph Curry's free throw shooting? So up here, X was binomially distributed with 4 coin tosses and a 0.5 success rate. That's the important thing to notice. Let's think about Steph Curry. Is his free throw shooting 100 times a binomial distribution? I have to check those 3 conditions. Are there a finite number of trials here? Yeah, it's 100 free throws. Right, so that would be my first number. The success rate is his free throw percentage, so 90.8%, 0.908. There's 2 outcomes. He can hit the free throw or he can miss it. This is the probability of hitting it. And then is each one independent and done under identical conditions? That's probably the only question mark, but let's just assume he's shooting free throws in an empty gym. His number might even go up. It's not unusual to be. You never know. He's inhuman. Okay. What's the expected value? It's always the number of trials times the success rate. So you take 100 times 0.908. I would expect, on average, he hits 90.8 of those 100 free throws. Again, not surprising at all when you think about what this percentage is supposed to say. What about the variance? Well, that's N times P times Q. So it's 100 times 0.908 times, so let's do this. If he hits 90.8%, then he misses 9.2%. And then once I take that product, I have his variance. Quick. 90.8 times 0.092. It's like 8.3536. And then if I took the square root of that, that's a little bit less than 3, like maybe 2.8-ish. That would mean he hits an average of 90.8 of these, and the standard deviation would be about 2.8. Again, pretty remarkable. Questions about those examples? Once you know you have a binomial distribution, and you know the 2 parameters, the n and the p, you can simply use these 2 formulas to find the expected value and the variance, and there's no other calculation required there. Now, here's an interesting question that is often asked. What if I'm looking at the Steph Curry situation, and I want to know what's the probability he hits 91 or more free throws? Right? I want to know, is he going to hit enough to start raising his average? You need to hit 91 or more to do that. Well, I can compute the probability that he hits 91, and the probability he hits 92, and the probability he hits 93, and so on, all the way up to 100, and add those numbers up. How many would that be? That'd be 10 different numbers to add together. Each one of those numbers can be computed with that probability distribution. I'd be 100 choose the number of hits times 90.8% to the number of hits times 9.2% to the number of misses. Okay? And so this is generally what that would look like as a formula. I want to find the probability that he hits 91 or more, so that my y variable here is greater than or equal to 91. So I add up all the values from 91 to 100 as the number of hits. 100 choose that number to pick which ones were hits, which ones were misses. I need that number of hits, and 100 minus that number of misses. So this is just applying that formula directly and then adding up each of the 10 values that you would need that correspond to each of those possibilities. 91 hits, 92 hits, 93 hits, all the way up to 100 hits. Okay. And I don't know about you, but that looks like a lot of work to calculate. So this is where calculators will come in and help us out a lot. This is the first place where we're going to be using Professor Bognar's calculators, the professor at the University of Iowa. So I will show you how to use his calculator to calculate the same things. All right. So by the way, show you his page in general. This is his web page, and he has a number of different distributions here. These distributions are available on iOS and Android in the usual app store, so if you want to do them that way, you can. But discrete distributions covers a number of different distribution types that are discrete random variables. We talked already about the binomial. In just a few minutes, we'll talk about Poisson. There are others here, and some of these are included in your textbook, but there are some that are, of course, not included here. Continuous distributions. We will be talking about the normal distribution and also the t-distribution in this course, and in fact, the f-distribution and the chi-square distribution. We will use this when we do confidence intervals and hypothesis testing. So each of these things will be very, very useful. I'm going to click on the binomial distribution. Let's do the fair coin toss situation. Let me zoom in so you can see this better. All right. So I'm tossing a fair coin, let's say 10 times. It's a fair coin, so I have a 50% chance of heads. And I'm asking, what's the probability that I get, let's say 7 heads? So the probability that x equals 7 is 0.11719. That's this number. And you can see how it compares to other numbers in the distribution. You can also see the expected value in this situation is exactly 5. And the variance is exactly 2.5. And then, of course, here's the standard deviation in the middle. Well, what if I wanted to find for Steph Curry? I know 8, that was his success rate. Well, there's a 0% chance he hits 7 and misses 93. That makes sense. Let's say exactly 91. There's that outcome. There's a 13.77% chance, 7-8% chance, I guess, that he hits exactly 91 free throws out of the 100. It's basically impossible for him to hit less than 80. Remarkable. Plenty of career averages well below 80. I think LeBron's like 70% or something like that, 72% perhaps. And he's still a star, so what can I say? Anyway, more importantly, if I wanted to do the question we just asked, what's the probability he hits at least 91? All I have to do is to change this drop down to say x greater than or equal to the 91. And it shades which ones it's talking about, and it nicely does the addition of each of those values for me. And so there's my result. The chances he hits 91 or more is 55.988%.
For your birthday.
Again, instantaneous on this exam.
Go outside.
What is the... Let me do it this way.
He left the door open. I don't know why, but he left the door open.
I won't. I'll have to do it a different way later on. There's a way to find the upper quartile, or the number of hits he'll hit in 100 tries, and you can find when this area is 25%. Do it manually, I guess.
Come inside and get my jacket.
Between 93 and 94.
Good point.
All right. Questions about that? I think that's what I had for the binomial distribution. All Alright, so just to recap really quickly, the things we saw, if you have two possible outcomes and a fixed number of independent trials, then you're usually going to want to use a binomial distribution to represent that situation. The number of outcomes is n, the probability of success on a single outcome is p, and with those two parameters alone, you can build a probability for a single value for your random variable. That's this formula. Feel free to just use Bogdanov's calculator to calculate it. And you can also compute an expected value from those parameters. The expected value is n times p, and the variance is n times p times q. You can even compute more complicated things like what's the chance my random variable is at least a given number, or at most a given number, or between two numbers. What are the chances he hits between 88 and 92 free throws? I can do that, and I would recommend using Bogdanov's calculator for that, because it will do the individual calculations and add them together for you. It also does the nice thing where you can visually see which bars are included, and you can then verify it's the ones you wanted to include. All right, any questions about that? All right, so we're running a little short on time. I don't want to rush us too much. I'm going to give us a 3-minute break. On my clock, it's 11:03. Let's return at 11:06, and we will talk about Poisson distribution, our second and last discrete one. See you in a few.